Hi, welcome back. Let's continue talking about properties of the continuous time Fourier transform. All right, so some of these again, I'm going to prove. Some of them they're just not worth our time to prove once you get the flavor of these. So I'm going to start again with proving differentiation in time. So suppose x has Fourier transform capital X of j omega. We want to know what So given that, what is the Fourier transform of a related signal, right? That is the derivative of x. Okay, so to prove this, I am going to prove this one. If x of t has Fourier transform capital X, then we can write x of t like this. We can synthesize it. D omega. Okay, now I can take the derivative of both sides. So this would be dx of t dt. And if I take the derivative of the right, the constant can come out in front. The derivative can go all the way into the integral, and since capital X does not depend on time, the derivative can go all the way to the e. So let me do that. So this is capital X, and then I've got the derivative e to the j omega t d omega, like that, right? Now, I've got the derivative of x of t on the left. This is 1 over 2 pi. And then the derivative of e to the j omega t versus with respect to dt, with respect to t, is j omega e to the j omega t. So that j omega then can come over here, j omega x of j omega e to the j omega t. Now the interesting thing here is that let's call this something like, I don't know, g of j omega, right? It's another function of j omega. So now what I've got is this guy. And so now you compare this to the synthesis equation. This looks like the Fourier transform, or this looks like the synthesis equation, right? So we conclude that the derivative of x has Fourier transform g, which is j omega times the original Fourier transform. So the property that we're looking for is this. This has Fourier transform j omega times the original. That's huge, it turns out. That's going to be a big one for us. This one is a big one for mathematics and engineering. This is why you use the Fourier transform actually in differential equations. We'll have more to say about this in future videos. Now, related to this is the differentiation in frequency property, and I'm not going to prove this one. I'm just going to give you the result. If x of t has Fourier transform capital X of j omega, then the derivative of capital X, okay, in frequency, so the derivative in frequency has the signal minus jt times g of t. That's the result. I'm not going to show you why, but let's analyze the results. This is actually from the duality principle. In differentiation in time, we took the derivative in time, and then in frequency, that's like multiplying by the independent variable, which is j omega, right? And so now the dual to that is differentiating in frequency is like multiplying by the independent variable in time, which is t, and then we pick up this minus j coefficient, or the constant. So you see how that works, right? There's a dual nature there between those two things. Okay, so let's move on. Time and frequency shifting. I'm just going to give you the result. If x of t has Fourier transform capital X of j omega, then the Fourier transform, sometimes we'll write it like this with like a script f, and that means the Fourier transform of. So the Fourier transform of, I guess I'll stick to the same notation I've been using. Let me do that. So if x has Fourier transform capital X, then x of at, right, where a is a constant, that has Fourier transform given by this. It turns out it depends on the sign, sign, of that constant. So it's this top one if a happens to be greater than 0, and it's the bottom one if a happens to be less than 0. If a is equal to 0, then this doesn't really make sense. X of 0 doesn't really make sense. And we can combine this then into one thing, 1 over the absolute value of a, x of j omega over a. So that's the result, right? That's the Fourier transform of this guy. So this is interesting to us as well, and this is actually demonstrative of the Heisenberg uncertainty principle. If a is, say, 2, x of 2t is a compression of the signal, so the signal gets squeezed by a factor of 2. But then notice the independent variable in frequency, j omega divided by 2, well, that's an expansion. So as you squeeze in time, as you compress in time, you expand in frequency. And if a was like 1/2, then this would be expansion in time is like compression in frequency. So again, that is the Heisenberg uncertainty principle. Actually, it's a marvelous principle. Anyway, moving on. Parseval's relation, I'm just going to give you the result, and I just want to comment on the intuition behind this result. Parseval's relation says the following. If I take the square of the absolute value of a signal and integrate it over all time, that's equivalent to 1 over 2 pi times, if I took its Fourier transform and squared the absolute value, like this. This is the relation, and the interpretation is as following. So do you notice or do you recognize the left-hand side at all? That's the total energy in the signal, right? So Parseval's relation says that the total energy in the signal may be computed by finding the energy per unit time and integrating over time, that's this, or by finding the energy per unit frequency, right, radians per frequency, and integrating over frequency. So you can find the energy in the signal in either discrete time or continuous time, or excuse me, in either continuous time or in frequency, in time or frequency. So this is no surprise to us, because we've been saying all along that there's an inverse transform, right? And so you lose no information. You can represent the signal in time, or you can represent the signal in frequency and get the process back. So you should be able to calculate the energy in either time or frequency, because you're losing no information. Okay, we have a couple more properties coming up. I'll see you in the next videos.